Hello, it's a pleasure to welcome you to this edition of Focus On Behind the Flight Deck Door. Focus On sessions are aimed at industry professionals and focus on a topic relating to aviation safety investigation by looking at it from a different perspective. The sessions are open to the public, and therefore we're only able to address general concerns and will be able to answer questions concerning will not be able to answer questions concerning a specific accident or personal experience. The topics covered today will include lithium-ion batteries, cabin safety considerations in accident investigation, disruptive passenger behavior, and its impact on crew well-being and flight safety, along with cabin evacuations and minimum cabin crew regulations. I'm Joann Sheehan. I am the current chairperson for the ISASI Cabin Safety Working Group, and I'm also a 37-year flight attendant for a major American U.S. carrier. Before beginning our session today, we'll do a few housekeeping items. We'll let you know that our session is being recorded. We'll ask you to keep your camera and microphone muted for the duration of the meeting. This session will be available on the ESASI website and after the presentation. And time permitting during our presentation today, we'll do our best to take questions, time available. We do ask that you follow the Chatham House rules. And if we are unable to answer the questions because of timing, they will be answered afterwards, and a full recording will be available on the ESASI website. The ESASI committee is mindful that there is a relatively short time frame, and we are aimed at providing a solid overview of the topic. So we won't be able to cover all questions. We apologize in advance, but we will make all questions available on the website after. And with that, we'd like to begin our presentation. Our first presenter will be Darlene McLaughlin. Darlene is the Technical Officer, Human Factors with the International Civil Aviation Organization. Darlene's career spans 35 years in aviation, of which 25 were as a civil aviation inspector with Transport Canada National Flight Operations. Darlene ended her career with Transport Canada as a Senior Policy Advisor to the Director General Civil Aviation before joining ICAO in March of 2023. Darlene?
Good morning, good afternoon, and good evening. I'm not sure if my camera has decided to not work for me right now, but if you can see me, great. If you can't, I'm so sorry. So I am so pleased to be with you today to provide a review of the cabin safety aspects in an investigation. And this presentation will provide an overview of the ICAO document 10,062, which is the manual on the investigation of cabin safety aspects in accidents and incidents. And the purpose of this manual was to encourage the uniform application of standards and recommended practices contained in Annex 13, Aircraft Accident and Incident Investigation, particularly in relation to survival aspects, and to provide information and guidance to the states on the procedures, practices, and techniques that may be used in aircraft accident investigations specific to cabin safety. It is also intended to complement guidance presented in a manual of aircraft accident investigation, incident investigation, so Doc 9756. And finally, this manual provides guidance to help operators investigate incidents which do not meet the ICAO definition of an accident, hence do not require an accident investigation by the state of occurrence, but which may provide evidence of hazards or deficiencies within the aviation system. Slide 2, please. So this overview today will present a review of cabin safety, past accidents and improvements, cabin safety aspects and investigations, and Doc 10,062, which I just referenced, and some of the overview of the contents and templates which may be found in that document. Next slide, please. So we are going to begin with a step back in terms of cabin safety and past accidents, and how the findings from these accidents then led to changes in survivability factors. So in image 1, which you'll see, this occurred in 1983, and this was a DC-9. During the flight, cabin crew discovered a fire in the aft lavatory. However, they were unable to locate the source. The crew made an emergency landing and initiated evacuation procedures. Soon after the exits were open, a flash fire engulfed the aircraft interior. Half of the occupants died. The investigation determined that the probable cause of the accident included cabin crew underestimating the severity of the fire and providing misleading fire progress reports to the captain. Some of the fatally injured passengers were found in the proximity to exits. In 1983, there was no floor path lighting installed in the cabin. This actually came as a result of this incident. The visibility had deteriorated so badly that the passengers were not able to locate exits in the dense smoke. Recommendations in the accident report included requirements for smoke detectors and automatic fire extinguishers in lavatories, and today they are a certification requirement. The need to review cabin crew training and procedures, including firefighting and crew resource management, and providing passenger instructions on how to open emergency exits as an international best practice. Still, it is not today, but we're working on guidance to recommend this based on industry best practices. In image 2, which is to the left of image 1, this is in 1989, a 737 that experienced a fan blade fracture in the number 1 engine. Believing that number 2 engine had suffered damage, the flight crew shut it down and diverted number 1 engine. Number 1 engine subsequently suffered a major thrust loss and the aircraft impacted a field. More than half of the occupants perished in the crash. The investigation cited that many people on board, including 3 cabin crew members, saw flames that had emanated from number 1, but never informed the pilots. This was deemed a contributing factor to the incorrect response from the flight crew, and so shutting down the wrong engine. During the diversion, the cabin made a PA explaining to passengers that the trouble with the right engine had produced smoke and it was shut down. The accident report noted that many of the passengers who saw the fire in the left engine were puzzled by the captain's reference to the right engine, but never brought the discrepancy to the attention of the cabin crew. Among the recommendations that the report stated was that training exercises for pilots and cabin crew should be introduced to improve coordination between flight and cabin crew in response to an emergency. So image number 3, if you wouldn't mind, please. In 1989, this was a Fokker F-28. The aircraft failed to gain altitude after its attempted takeoff and crashed. A third of the passengers and 3 crew members, including the captain and the first officer, and 1 of the 2 cabin crew members were fatally injured. Contamination on the wings resulted in loss of control. The final report into the accident noted that 1 of the cabin crew members and several passengers had noticed ice buildup on the wings, but failed to transmit this information to the flight crew. Poor crew resource management and deficiencies in cabin crew training were also cited as contributing factors. Recommendations included the requirement for each operator to provide to the competent authority an operator cabin crew manual, either as part of its operations manual or as a separate manual, and the need for regulations setting the training and competency requirements for cabin crew. Image 4, please. 1991, and a 737. Upon landing, the aircraft collided with a small turboprop and caught fire. all 12 occupants on board the turboprop, as well as a quarter of the passengers and 2 crew members on board the Boeing were fatally injured. Several passengers seated aft of the overwing area who made their way to the rear of the cabin reported using the emergency floor path lighting. This improvement was a result of the earlier DC-9 accident. The accident cited as a finding that the exit row briefing provided by the operator of the 737 increased the preparedness of passengers for the evacuation. Many of the fatally injured passengers on the 737 were found near the overwing exit, which was partially blocked. They did not proceed to other available exits in the rear of the aircraft and were overcome when the cabin fire intensified. And this is why you may notice that cabin crew typically point out alternate exits during a briefing, which passengers do not always recognize as a means to evacuate. Image 5, please. 2005, and a 737 which failed to pressurize due to maintenance issues. As the aircraft climbed, the cabin altitude warning horn sounded. The flight crew misidentified the warning as a takeoff configuration warning and attempted to troubleshoot. Meanwhile, the oxygen mask in the cabin automatically deployed, and it presumed that cabin crew became aware of the decompression. However, the aircraft continued to climb, and both flight crew members succumbed to hypoxia. The aircraft continued to fly on autopilot until it suffered from fuel exhaustion and crashed, and there were no survivors, and the aircraft was destroyed. It should be noted that cabin crew are, or should be, trained to know that a decompression is followed by a rapid descent. The fact that the aircraft kept climbing should have been a clear indication to them that there was a problem. In fact, the investigation concluded that one of the factors that could have contributed to the accident was the lack of cabin crew procedures to address events involving loss of pressurization and continuation of the climb despite oxygen mask deployment. As a follow-up to the accident, EASA issued a Safety Information Bulletin 2009-33, which recommends that operations manuals should be reviewed and amended to address such procedures. And number 6, please. In 2005, and an A340 with 297 passengers and 12 crew members on board, which overran the runway after landing, went down a ravine and caught fire. All passengers and crew members were able to evacuate the aircraft before the fire reached the escape routes. A total of 10 passengers and 2 crew members were seriously injured during the crash and the ensuing evacuation. It should be noted that passengers included 8 children, 3 infants, 3 wheelchair passengers, and 1 visually impaired passenger. So this makes the evacuation even more challenging. The accident report noted that the evacuation was impeded because nearly 50% of the passengers retrieved carry-on baggage. The report also stated that the evacuation was successful due to the training and actions of the whole cabin crew. In general, the performance of the cabin crew was deemed exemplary and professional, and was a significant factor in the successful evacuation of the aircraft. The report cited effective communication between the flight and cabin crew members, and this report accident highlights the importance of cabin crew training and cabin safety. Next slide, please. So, in retrospect, when we look at the improvements that have occurred in cabin safety over the past 30 years, this slide highlights some, and references also made in Doc 10,062 about these improvements. So it's highlighted by some of the cases presented in the previous slide. Accident investigations have led to significant cabin safety improvements over the past 30 years. These improvements have helped increase the survivability of occupants involved in subsequent accidents. Some of the improvements cited on the image come from accidents previously referenced. Beyond crew procedures and training, improvements include 16G seats, so passengers remain passenger seats remain in their track in an impact. And a 16G seat is tested in a manner that stimulates the loads that could be expected in an impact survivable accident. Fire retardant materials to reduce toxic fumes in the event of an in-flight fire, and exits design, such as automatically disposable hatches instead of the conventional Type 3 overwing exit for new aircraft types. That removes manual intervention to ensure that the hatch's final location after opening does not impede the evacuation path inside or outside the aircraft. So as we prepare to emerge and delve into Doc 10,062, one thing that I think, after the 35 years in this industry, it's quite apparent that my experience has been that when beginning an investigation or reviewing the reports, the investigation task process may seem arduous at first and overwhelming, but the benefits to be gained from the systematic and thorough investigations makes the effort worthwhile. And one only has to examine the steady improvements in system safety to appreciate the benefits to be gained. Next slide, please. So this source of data comes from the ICAO website on EDREP, and it shows that most occupants survive accidents. The fact that most occupants survive accidents can be linked to improvements made in occupant protection. These improvements result from survival factor investigations, which address cabin safety aspects during accident investigations. So again, in looking at the slide, and you can choose to also look at the ICAO website to take a look at the taxonomy, because it is listed there as well. It shows, the survivability rate of accidents. Next slide, please. So, the cabin safety aspects and investigations. Cabin safety aspects should be addressed as part of the investigation. So, approaching an investigation using a systems approach encompasses all affected areas of an investigation, of which cabin safety is an important element. And the analysis, when we look at the cabin safety related aspects, can provide valuable insight into issues such as systems engineering and design, human psychology, human factors, and all of its subfields such as ergonomics and biomechanics, human performance and limitation, human cognition, behavioral psychology, organizational psychology, learning psychology, and more relating to cabin crew, passenger, the aircraft and its system and equipment, and any limitations. Next slide, please. So the document itself is in its second edition as of 2022. It was first published in July 2016. And it was the first ICAO manual dedicated solely to cabin safety and investigations, and it supports Annex 13 and also the previously referenced document in my introduction, 9756. It provides detailed guidance focused on cabin safety aspects. So the accident investigation and cabin safety improvements, cabin investigator competencies and training, accident investigation and cabin safety, and incident investigation of cabin occurrences. Next slide, please. In terms of the competencies for the cabin investigator, the document provides guidance to states and users on the role of the cabin investigator within the investigation process, the recommended qualifications and responsibilities, the competency framework and skills, training specific to the role, and also that the cabin inspector may be employed by an independent accident investigation authority, state or operator, And chapter 4 of this document is that these roles can be adapted to, states that chapter 4, which is the competencies and trainings element, can be adapted to any of these roles. So as an idea of what the contents relay in terms of recommended qualifications of the cabin investigator, the document states that the recommendations, the recommended qualifications include, but are not limited to, the ability to investigate, document, and analyze issues pertaining to contributing factors in aircraft accidents and incidents, current knowledge of and experience in evaluating aircraft cabin interior configuration and certification, emergency equipment requirements, design and certification, cabin crew safety and emergency procedures and related training, cabin safety, occupant safety, knowledge of survivability principles, seats and restraint systems, and the list goes on. Next slide, please. And the types of occurrences. So events classified as accidents as per ICAO's definition, and there we go. We can just bring up all of these. Evacuations, ditching or inadvertent water contact, fire, smoke, and or fumes, turbulence, decompression, aircraft damage, fatal or serious injuries, which is miscellaneous. And chapters 5 and 6 of the document provide more elaboration on these types of occurrences and their respective investigation process. Next slide, please. The document also provides a template for investigation, which explains what to gather, the specific info, and why, the objective. And detailed templates cover all of the areas. So we should have about 6 little, we've got general information, documentation, aircraft information, human performance, additional information, and then the conduct of interviews. Next slide, please. So documentation refers to the occurrence specific documentation and from the following sources. So this is the collection of the relevant documentation from the operator, the state of the operator, and other sources. For example, the aerodrome where the accident occurred. Next slide, please. The document also relates to, in terms of operator documentation, the need of the cabin investigator to evaluate the air operator policies and the standard operating procedures. So this would be documents relevant to the occurrence and actions expected of the crew. So the training programs, for example, to the evaluation of the operator training program to assess the content and the adequacy in preparing the cabin crew, and additional operator documents, which may provide insight into organizational factors such as training records, logbooks, and the rostered duties. Next slide, please. In terms of aircraft cabin information, this is the collection and the documentation of the cabin as a key part of the investigation process. So the cabin investigator needs to examine and record condition of the relevant aircraft systems, safety and emergency equipment, and the cabin in general. And we'll move to the next slide, please. And in terms of the relevant aircraft systems and equipment, so this chapter lists the specific systems and equipment to document, the specific to occurrence, the specific information related to the occurrence, and the templates of what to record, such as the presence and condition, and why. And the why part is to evaluate if the systems were useful in managing the occurrence, determine if the 6 systems worked as intended, evaluate the type of equipment available, and assess if it was useful or a hindrance. So the analysis should focus on the reasons for failure, damage, or malfunction of structures, systems, equipment, and or components, and evaluate how they affected the ability of the crew members to carry out their duties and responsibilities, and the survivability of occupants involved in the occurrence. And this process may require testing of parts. And the question that's often asked is, did the equipment or system operate as intended? Next slide, please. The conditions of the cabin. For the conditions listed in the cabin in Doc 10,062, the cabin investigator should record the presence of condition if there was failed, damaged components, serviceable, and or if the components work normally, the part and serial number of any affected equipment as well. And again, the reason why is to evaluate the reason for failures, damage of that specific or piece of equipment or system, and how this impacted the survival of occupants, and how it may have contributed to injuries, and whether or not the system or equipment affected the ability of the occupants to evacuate. Next slide, please. So human performance evaluates how the cabin crew performed and how the passengers performed. So the operational factors include aspects such as the cabin crew's knowledge of systems and equipment, their experience level and proficiency, crew compatibility, supervision, command, and control of passengers' action, and then the passengers' actions and responses during pre-flight activities, for example, where the passengers listening to safety briefings or actually took out the safety feature card, the passengers' behaviors and reactions during the occurrence themselves. And one of the previous examples at the beginning of this presentation was the fact that passengers ended up taking their carry-on baggage and subsequently slowed down the evacuation process. Any difficulty that a passenger may have had or passengers had in opening exits, getting to exits, and post and accident actions, such as responses to instructions from personnel, such as rescue and firefighting personnel. Next one, please. So, additional information. The purpose of any additional information as the underpinnings of the investigation process is to gather any insight into cabin safety aspects or survival factors. So gathering information on the post-accident investigations. So this may be emergency response, search and rescue. The analysis should examine how, for example, the rescue services responded to and managed the occurrence. If search and rescue operations were undertaken following the accident, the investigation or the analysis should also focus on the operations, the response, and how the incident was actually managed as well. Next slide, please. And then we're into the interviews. So again, this document provides an exhaustive content of information on the conduct of interviews, and the investigator or the cabin investigator conducting the interview should gather information which is accurate, complete, and detailed as possible. So again, quite a considerable amount of information contained in the document to guide the user on the conduct of the interviews, including the persons to be interviewed and all of the specific questions. And the chapter also the document also contains how to write the report, what should be in the report, and the process for the actual drafting of the report as well, and the fact that it needs to be factual. I'm cognizant here that this is taking a little longer than we originally, so I'm going to kind of keep moving. And then finally, this document also contains information for a complete chapter to operators on incident investigation. So this chapter focuses on investigation of incidents which do not meet the ICAO definition of an accident and may not require a formal investigation by the state of occurrence. But incidents can provide evidence of hazards or deficiencies within the aviation system and should not be overlooked. And there are several examples of these provided in that chapter as well. And next slide, please. So as I wrap this up, so I thought I would end by closing with the words of one of my mentors. So when I originally started in aviation, I came in as a flight attendant and then started Transport Canada as an inspector with cabin safety standards. So some of the names today, I'm like, we've been around a very long time. And one of my mentors when I started, and her words are actually on the Transport Canada website as well. And I thought, wow, I thought I'd end with that, is the summation of cabin safety's goal. And specifically when we're looking at the survivability, is that cabin safety's goal is aimed at increasing the survival rate by minimizing hazards in the cabin and its environment to reduce the effects of an accident. And subsequently, we have illustrated the improvements made through the analysis of cabin investigations, the importance of the cabin crew member. So in closing, I would like to thank you all for your time and your attention. I apologize for going over the limit to my fellow presenters. And the last slide provides my contact information. And again, thank you for your time, and I appreciate the opportunity to talk with you today.
Thank you, Darlene. We appreciate it. The presentation was full of information, and it did run long. And so in order to keep things on track, any questions that have come in, we're going to have to answer those after we've completed today, and they'll be online, available online. Our next presenter is Mr. Jean-Paul Vieux. He is with Airbus, and he'll be discussing the minimum number of cabin crew. Jean-Paul has been with Airbus for more than 40 years, working in various areas from manufacturing to flight operations. Since 2008, Jean-Paul has worked in the Flight Operations and Training Support Department as a senior cabin operations engineer. He's also a cabin safety representative within Airbus Flight Operations. Jean-Paul?
Hello everyone. We will start this presentation by a simple question. Why do we need a minimum cabin crew number? So can you move forward? We will try to answer the question. Emergency evacuation are dynamic and highly stressful events for cabin crew. As you may know, cabin crew are required to manage the complete evacuation process. That means for them to manage the emergency exit by opening the exit, but also by not opening the exit in case of a direct threat. They require as well to permanently monitor the situation that may evolve because it's very dynamic, to manage the passenger, to communicate with the cockpit, and of course with the other cabin crew. During an evacuation, the number and location of cabin crew has a direct impact on the success of the emergency evacuation. So in this presentation, we will see how Airbus, the TC holder or the manufacturer, define the minimum cabin crew required, but also the other factors that may influence this number. Can you move forward, please? Next. Next. The minimum number of cabin crew is based, as you can see, on a lot of requirements that come from the aircraft type, the customized cabin certification, the operational rules, the compliance with the direct view, the door type and the door number, and as well the emergency evacuation demonstration and the associated evacuation procedures. Can you move forward again? Thank you. For the type certification, the TC, Airbus has to demonstrate that an aircraft can be evacuated within 90 seconds. And this is in accordance with the EASA CS25803 emergency evacuation. This evacuation demonstration is performed with the minimum required crew for the cabin and the cockpit that is based on the type of the exit and the maximum number of passengers that is eventually distributed in the cabin. The maximum seating capacity is, of course, limited by the available space in the cabin and by the type and the number of exits. Next slide, please. The type of door may also influence the minimum number of cabin crew. As an example, for type A exit, one cabin crew must be positioned in the cabin attendant seat, the CAS, adjacent to the exit, so they can reach the exit before any passenger. For type 1 exits, it's slightly different. One cabin crew must be positioned in the CAS installed next to the exit. When the aircraft is certified, as a result of the TC, the type certificate, the aircraft is provided with a type certificate datasheet, the TCDS. And this TCDS will record and contain the maximum passenger seating capacity for a given model or aircraft, and as well the minimum cabin crew as it has been demonstrated during the evacuation demonstration. Next slide, please. As you may know, aircraft cabin can highly be customized. So, during the customization process, the operator should select a cabin layout that complies with the TCDS. What does it mean? That means that the number of passenger seats must not exceed the approved maximum number of passenger seats, and as well that the number of cabin crew must be equal or above the number approved during the type certification. We will see that in certain cases, the minimum cabin crew may be higher than the number defined in the TCDS, and this higher number will come from the individual cabin certification. Sorry, because as part of the parameter to take into account for the customized layout, there are direct view of the cabin area. So in accordance with the CS25, seat, berth, safety belts, and harnesses, the direct view cabin attendant seat must have visibility on the main aisle and a certain percentage of the passenger seat from the unoccupied CAS during takeoff and landing. And as well, the fact that cabin crew must access the communication system. Can you move forward? I think we swapped two slides. Can you go back, please? So, sorry for that. Can you move forward? Okay. Sorry. Okay, can you go move forward? Sorry for that again. In addition, there is certain items that are installed that may require amendment to the regulation. And these amendments as well are published in the TCDS. As an example, additional cabin crew may be required that will increase the minimum required of cabin crew. And this is the case as an example for type A+ exits, when the third cabin crew is required for a pair of type A+. So I will explain. Airbus has succeeded to certified exits with a rating of 120 passengers instead of 110 for a normal type A exit. In that case, we have demonstrated that the third cabin crew is needed to complete the evacuation. That's why this for type A+ exit with a type rating of 120, we will have an extra cabin crew, and this will impact the minimum cabin crew. As well, in certain regulation, cabin zone with mini suite where have an additional cabin crew required for the zone because of the workload. Can you move forward, please? One of the questions we often receive from the operator is, can we reduce the minimum number of cabin crew? The answer is yes, in theory, for specific cabin layout. The minimum number of cabin crew may be reduced permanently, but this will be based on appropriate demonstration, because during the corresponding certification exercise, we could have an evacuation analysis requested or test of combination of both. In this case, this will be a major change to the design. And this major change will be required via an Airbus major modification or a supplement type certificate obtained by an approved design organization. At the end, both must be approved by the EASA. Can you move forward? The operator, on their side, should comply with the ORO CC 100, stating the minimum number of cabin crew shall be the greatest among the following. So the number of cabin crew established during the aircraft certification process, in accordance with the applicable certification specification. That means the number which is written on the TCDS, or one cabin crew member every 50 or fraction of 50 passenger seats installed on the same deck of the aircraft. That means, as an example, that for an aircraft with 4 pair of doors and a seating capacity above 400, the minimum cabin crew will be increased. Can you move forward, please? In operation, the minimum number of cabin crew may be reduced in accordance with the EASA ORO CC 205. As an example, it could be reduced in unforeseen circumstances when cabin crew is incapacitated or unavailable. It should be noted that any reduction in cabin crew operation must be reported by the airline to their National Aviation Authority. Here, once again, this is operator responsibility to ensure that first, an equivalent level of safety is achieved. A senior cabin crew member is always present on board, and at least one cabin crew member is required for every 50 or fraction of 50 passengers present on the same deck. Now we'll go through an example. This is an example of a typical twin aisle layout. It's a 3-class layout with 253 passenger seats installed. So as per the Airbus policy and reflected in the TCDS, there is one cabin crew for each door at floor level. So in that case, the minimum cabin crew will be 8. But due to the cabin customization, an extra cabin crew is required at door 2R to comply with the direct view. Therefore, in that case, the minimum cabin crew for this layout will be 9. So now it's time to conclude this short presentation. With this presentation, we hope that it's now clear how the minimum cabin crew is calculated, but also the direct impact that this number may have on cabin crew performance during an emergency evacuation. Bearing in mind that minimum cabin crew is a key element in cabin safety. So if you want further detail, we encourage you to have a look on the Airbus Win platform. This is an open platform that is produced by Airbus, where you can find various presentations on very interesting cabin subjects and flight top subjects, and this will include the minimum cabin crew. Thank you for your attention, and I apologize for the little mismatch in the slides.
Thank you, Jean-Paul. We do have one question
Yes.
that, if you have the time for, do you think that airlines focus more on briefing passengers on how to operate the overwing exits, but don't put much focus on what should be done after going out and how to help directing other passengers?
You mean you are talking about the briefing, but the
Yes.
briefing. The briefing is
Yes.
not. This is not a manufacturer issue, to be honest, because as per the ops, the briefing is mandatory to be done, but it's a pure airline issue.
Okay. Thank you very much.
Sorry.
No, it's okay. Thank you very much. I think that's it for the questions that we have that have come through. And with that, we will thank you very much for your time and your effort. And we will move on to our next presentation, And our next presenter will be Susanna Chin. Susanna's educational background is in psychology, mental health, and human factors, with over 20 years of working in a variety of roles and different industries. Her current role in Cranfield University is focused on apprenticeship, MSc in aviation, safety management, risk and regulation, which they run in collaboration with the UK CAA and the CAA's training body. Last year, Susanna project managed the running of an evacuation trial, which were designed by the University of Greenwich.
Good morning, afternoon, evening, whichever part of the world you are. My name is Joann Sheehan. I work for Cranfield University, and it's a great pleasure to be in here. Some of you might already know Cranfield University has a long history of running evacuation trials, history that's very much spanning almost over 4 decades. And the interest in running evacuation trials at Cranfield was sparked by the 1985 Manchester accident, which caused an increased focus in emergency evacuations. The significance of this event, where unfortunately 55 people lost their life following an engine fire during takeoff from Manchester Airport, Cranfield University undertook a detailed study into aircraft evacuations on behalf of the UK regulator, Civil Aviation Authority. Many aspects of emergency evacuation were looked at, and one of the very dominant one was passenger behavior. And the results were actually really, really interesting because even that it was very controlled testing environment and very little incentives were given to the people participating in the trials. The people actually behave really quite aggressively and compete with each other during the emergency evacuation. This research was led by Professor Helen Muir and had a major impact on air passenger safety. Many research projects then were run and conducted. A number of papers were published by different agencies like the UK CAA, the FAA, and Canadian TCCA. Following on from the work that has been previously done in Cranfield in relation to evacuation trials, last year Cranfield and the University of Greenwich ran a number of evacuation trials. And I thought it might be actually really quite interesting to walk you through some of the why, how, and what to consider when you project managing the running of evacuation trials. If you can move to the next slide, please. And this is some of the how, why, and what. If you start with why, it's very much about why would you run evacuation trials? What's the purpose? Well, most of the times the main purpose would be safety and perhaps improvement of safety, if that's done by testing existing procedures, how effective they are, and what improvements can be made. Testing of new procedures, introduction of new technologies, introduction of new layouts of the cabin and a new type of planes, explanation and testing of human behavior, how humans behave in a particular setups during different situations. And as previously mentioned, accident investigations, running a simulation that's very much based on a previous accident can provide us with further explanations and some of the lessons learned, that they are not just relevant for now, but actually for the future. The next point to consider is perhaps the what. Same as with any projects, it would be budget, location, facilities. It's good to consider what facilities are perhaps already available. If there is a facility that already would be suitable for running the trials, or if there is actually need for a new one to be built. Same as with any project, external and internal communication between the stakeholders, incredibly important. Something like insurance, ethical approval, GDPR, how are you going to deal with people's personal details, risk assessments, all of that needs to be in place. And then we move on to recruitment of participants. What rewards and incentives are you going to use to entice for participation in your trials? What systems and procedures do you need to have in a place to be able to run evacuation trials? And essentially what the timeline for running the trials would be. Then we move on to how. Are you going to run the trials themselves, or would you have any kind of pre-trial exercises? Media coverage, in terms of media, can be actually really quite helpful in terms of recruiting your participants, especially if you're looking for recruiting general public participants. But that can perhaps also hinder some of the running of the trials themselves. The design of the trial, are you going to make them competitive? Therefore, are you going to offer participants extra incentives if they perform in a particular way, or non-competitive? What emergency situation you will use? Are you going to use smoke in the cabin, fire, water? All of this is something that needs to be considered and discussed in the ethical approval as well that you put in place. And the very important part, your participants. Some of the work that has been previously done by Helen Muir, the participants used in there were essentially students of the university, perhaps raises the question of how representative university students are in terms of demographics of a general public. That's mean the use of certain demographics and perhaps preference of particular groups of participants for your evacuation trials should be considered. This is very much in a nutshell some of the key observations done through the project management of evacuation trials. And now I will hand over to my colleague Ed Galley from the University of Greenwich. Over to you, Ed.
Thank you very much, Susanna. So I'm going to share my screen. If you bear with me a minute. And I hope you can all see my slide. So I'm just going to start off with a brief introduction as to who we are. I basically started the Fire Safety Engineering Group back in 1986, and this was a direct result of the Manchester Boeing 737 fire. Today, we are a team of about 18 full-time researchers, and we're a combination of fire engineers, computational fluid dynamics specialists, mathematicians, psychologists, physicists, and software engineers. And what we do is we study how people react in emergency situations, primarily during evacuation, in a whole range of different types of enclosures, including aircraft, of course, buildings, ships, trains, basically anything that contains people. And we study the way people react and behave. We use this knowledge to build computer simulation tools, which we can then use to help to design safer environments. And that's what we've been doing for quite some time. And a lot of our work was done in collaboration with Cranfield on aviation, in particular with Professor Helen Muir, who we worked with for many years. What I want to show you here is just a collection of some of the experiments I've been involved with over the years. Some of these with Cranfield, for example, the bottom left is some work we did with Professor Muir, looking at how people would evacuate from an upper deck of something like an A380. The middle top is showing some evacuation trials, again, we did with Professor Muir at Cranfield University, looking at how people would evacuate from the upper deck of a A380 going down to the lower deck to use the lower deck slides. This was part of a EU-funded project called VER. The top right shows you some more experimental work we were doing, this time with Airbus, and here we were looking at how people would react in a smoke-filled environment and how they would try and trying to find the way out of an aircraft. And the bottom right is an example of some evacuation work we did again with Cranfield and Professor Muir, and I'm going to talk about that in my next few slides. So I mentioned we have software tools. We have the Air Exodus software tool that simulates, predicts how passengers behave in emergency situations, not just certification tests, but real accidents where you can involve fire. For example, we have a fire simulation tool called Smart Fire, which simulates how the fire spreads. We can link the two together, and in our simulation, we can expose the agents to the developing fire environment so that we can see how they would react and behave in a fire situation. So what I want to move on to for my last couple of slides is basically show you some work we did with Airbus as part of an EU-funded project called NACRA. And here we were looking at how could you evacuate over 1,000 passengers from a blended wing body aircraft? And we did the first computer simulations of this and demonstrated that it was possible to get everyone off in 90 seconds. In this particular aircraft, we have something like 20 exits, and we had a minimum of 25 cabin crew, one cabin crew member at each of the floor level exits, plus 5 additional cabin crew in the cabin to direct traffic. Now, one of the things we found in our computer simulations that even though we could get everyone out in 90 seconds, we found that the rear exit in the corner was highly underutilized, and it was not really attracting as many passengers as one would hope or expect. When we presented these results, there was some disbelief from Airbus and from the regulators, saying that they didn't believe that would happen, and so cast into question the credibility of the particular simulation here. And so what we did was, in collaboration with Cranfield and as part of this project, we built a simulator of this cabin, a partial simulator. I identified the part of the cabin that we needed to do and the types of experiments we needed to do. And then we ran those experiments to see what we would come up with. And so these were run at Cranfield University in collaboration with Professor Helen Muir. And in the bottom left image here, I'm just showing you some of the passenger participants we had. We had over 300 odd passengers for each trial. The top left video is showing you a walk through our cabin simulator at Cranfield, showing the part of the cabin. And the video on the top right is actually showing you one of the actual evacuation trials that we were running. And it's that exit in the corner that you can see at the top left. This is the one that was causing the issues in our model. It's exit E6 that's located in the image here. And what we found in the simulations, as I said, was very few people use that exit, but we could still manage to get everyone out in 90 seconds. And in my last slide, what I'm showing you here is a comparison of the model predictions against the experimental results. The blue columns show the number of passengers to leave by each of the exits, and the red columns show you what we measured in the experiment. And here we have the exit E6, where we were predicting very, very few passengers using that exit. And you can see the trend as you move away from this exit, you get more and more passengers using the various exits. And this is precisely what we found in the experiment. So the experiment verified what the model was predicting, gave Airbus and the regulators much more confidence in the ability of the model to predict this very complicated situation. And basically it was thanks to the work we did with Professor Muir at Cranfield to collect the evidence to support what the model was actually predicting. That's the last of my slides. I hope I've given you an idea of some of the modeling work we've done and how we've worked with Professor Muir at Cranfield to collect evidence to support our modeling. Thank you very much.
Thank you. You've done a great job. And we do have a couple questions if either you or Susanna wishes to answer them. Is there any guidance that examines the clothing worn by the participants in the evacuation studies? And are there minimum clothing requirements for the passengers to use the evacuation slides without getting friction burns? So that's a two-part question.
Yeah, I mean, from our experimental protocols and also in the ethics review that we have, we try to minimize the possibility of injury of all the passengers. So we stipulate, for example, the passengers should wear flat shoes, they shouldn't wear heels, they shouldn't wear loose-fitting clothing. We don't allow them to bring luggage or baggage or handbags along in the trials. So we really try to minimize the potential impact of injury. Now, not all of our trials involve using slides, and the most recent trials that Susanna mentioned that we ran at Cranfield a few months ago, they also didn't involve slides. So we weren't concerned about the potential impact of friction burns and so on. But when we do run those trials, we do take that into consideration as well. We try and minimize we ensure that the passengers have got, or the participants have got very minimal exposed skin exposed while they're participating in the trial. So no shorts, no short sleeve shirts, and that sort of thing.
Okay. The next question we have is, do the computer models use data from real trials and accidents to predict how humans will behave?
Yeah, so we've used, in fact, we've had quite extensive access to virtually every single certification trial that's been run in the past. We've managed to get all the video footage, and we've analyzed each of those frame by frame by frame. And so we've collected a lot of data there that we utilize in our model. So I believe our model is one of the few that can actually predict how people use particular types of exits, because we don't simply assume an average flow rate. We have what we call passenger exit hesitation times. So it's how long people hesitate at the exit. And we also use data from trials, not just the certification trials, but from the experiments. I showed you a video of some work we did with Professor Muir concerning the upper deck of the A380. And so we were collecting data from there about the hesitation time of passengers at the upper deck. And we also use data from accidents. We do, in fact, we validate our models using data from accidents. And a paper we published a few years ago, we demonstrated we could predict the number of fatalities in the Manchester 737 fire from 1985. So we use accident data, but primarily to demonstrate we can predict what happens in those accidents.
All right, thank you so much. With that, I think we'll be moving on to our next presenter. Our next topic will be the ion lithium battery fires. And we will be joined shortly by Lisa Fitzsimmons of the UK AAIB. Lisa is a senior inspector of air accidents and engineering at the UK Air Accidents Investigation Branch, where she has worked for 14 years. She was the lead engineering investigator on an AAIB investigation into a lithium battery fire, which originated in the emergency locator transmitter of a Boeing 787 aircraft. Today, she's going to provide a technical introduction to lithium batteries.
Good day, everyone. So I'm going to provide a short technical introduction to lithium batteries, how they work, what happens inside a battery cell, what happens when a battery experiences a failure, and how that can represent a threat in the aircraft cabin. Next slide, please. So I'll start with the definition of a battery. A battery is essentially a stored energy device consisting of one or more electrochemical cells that convert chemical energy into electrical energy. In the case of a lithium ion cell, that will consist of a negative electrode known as the anode, a positive electrode known as the cathode, an electrolyte, typically a liquid, that allows movement of the ions within the battery cell, and a separator membrane that electrically insulates the electrodes inside the cell. They will be connected to terminals that allow current to flow out of the battery into an electrical circuit and perform work. Next cell, please. So why use lithium? The graph at the top of this slide shows the increase in use of lithium globally over the first 2 decades of this century. And that rise in lithium use is driven almost entirely by battery use. And the reason for this is that lithium offers a lot of advantages in terms of its energy density. That means you can get a lot of energy out of a small volume of material. And this is particularly appealing to portable device manufacturers. Low maintenance requirements, and high durability are other benefits of using lithium. But there are some limitations in that lithium is reactive and fragile, and when used in batteries, circuit protection is needed to maintain safe operation. Next slide, please. So just to provide a more specific definition, a lithium battery refers to a battery where the anode and cathode materials serve as a host for lithium ions. The battery stores and releases energy by moving these ions from the anode to the cathode when the battery is discharging, i.e. when it is providing power to a device, and from the cathode to the anode when the battery is being charged. Lithium-ion batteries are all rechargeable batteries. Next slide. This slide shows 3 typical lithium-ion cell constructions that are available in popular consumer electronics and carry-on PED devices. A battery can be comprised of 1 or many cells. They contain positive and negative electrodes, as we've already discovered, and the construction shown in the slide shows how these are assembled together in the battery. A key component is a thin membrane known as a separator, and this is typically a thin polymer film which divides both sides of the cell to keep the cathode and the anode material from physically coming into contact with each other, and therefore providing electrical insulation, because otherwise this arrangement could result in a short circuit. The separator is a critical component in battery design. The cells also include liquid electrolyte, as we've alluded to. Next slide. So in terms of how a battery works when it's undergoing the electrochemical reactions, the ions will move through the electrolyte and they will pass freely through the separator membrane in the cell. The separator, however, acting as an insulator, prevents electrons from passing through the cell, and these electrons are forced into the external circuit. The movement of ions creates a voltage drop across the battery terminals, and this is what allows the electrons flowing in the external circuit to provide an electric current. So the top image shows a light bulb illuminated. It may be a phone or another device that the battery is powering. However, when the lithium battery is being recharged, application of external electrical power will reverse the reaction. The ions will move in the opposite direction inside the cell, and the electrons will travel in the opposite direction through the circuit. The movement of ions through the electrolyte and electrons around the circuit are interconnected and interdependent processes. One cannot exist without the other. Next slide, please. So that's all very well when batteries are working as intended, but there are many possible issues that can arise, and I think we're well aware of lithium battery failures. Lithium itself is an extremely reactive material, and there is often a lot of energy packed into a small space in a battery cell. The construction of the cells and their operation allows this energy to be extracted rapidly, which is good when that has been done in a controlled manner, and less good when that happens in an uncontrolled fashion. Lithium is susceptible to heat. The base material has a melting point of 180 degrees Celsius, and molten lithium will react violently with just about any other material. Precautions are therefore necessary in the design and use of lithium batteries to avoid an increase in temperature, which might assist lithium in reaching its melting point. And thermal stability is therefore a key criteria in battery design. The liquid that forms the electrolyte is often also a highly flammable material. Next slide. If temperature was to increase within a lithium battery cell in such a way that it was unable to dissipate from the cell, and a phenomenon known as thermal runaway will be encountered, in which the cell enters an uncontrollable self-heating state. The cell generates heat at a rate several times higher than it is able to dissipate heat. It can result in violent cell venting, where the contents of the battery are released as smoke, flammable gases, open flame, and often cells explode. Temperature rises can be in excess of 1000 degrees Celsius. Think of it as all of the energy in a battery cell being released at once in an instantaneous and uncontrolled fashion. Most battery packs are comprised of more than one cell. So if one cell goes into thermal runaway, it can cause a temperature increase in neighboring cells and propagate the thermal runaway into a cascading reaction throughout the battery pack. Next cell. So things that can cause a thermal runaway typically arise from faults or defects, either externally in the battery circuit or internally within the battery itself. Batteries are susceptible to any form of abuse, whether that be mechanical, electrical, or temperature. And some of the typical failure modes are listed on the slide here. One example may be an internal short circuit within the battery. We mentioned the separator material earlier, and this is a thin and fragile material. Any degradation in that material can lead to a short circuit occurring if the separator is punctured, torn, compromised in any way, or melted due to excessive temperature rises. Some batteries have external protection devices to limit the potential for short circuits. However, examples have shown that these can be overcome. If a battery, next click please, if a battery was to be used in an aviation application, those batteries require to be subjected to various abuse testing to demonstrate how they behave in thermal runaway, whether the battery can prevent whether the battery can be prevented going into a thermal runaway, and if it does enter a thermal runaway, how the effects of that runaway can be contained. So these tests will include crushing a battery cell, driving a nail through it, dropping it, subjecting it to mechanical vibration or shock, or immersing it in water. The cell may be over-discharged or overcharged, or it may be subjected to external sources of heat. But it's important to remember that many batteries that power our electronic personal devices may not be subjected to such rigorous testing. Next slide. Whatever the type of failure, whether it be an internal or external short circuit or a charging or overcharging issue, all of these failure modes have a common feature that they lead to elevated temperature within a battery cell. This in turn generates a buildup of heat and gas. If the heat, as we said, can be dissipated, then it is possible to reach a safe outcome. If not, the cell will progress into thermal runaway. The battery will vent, rupture, and will experience a release of fire and flames and potential explosion. As heat is the predominant characteristic in a thermal runaway reaction, it's perhaps not at all unsurprising that it is important when tackling a lithium battery fire to first and foremost reduce the heat and take any heat out of the reaction. Fire extinguishers can be used on open flame, but are typically ineffective in reducing the heat in a lithium battery fire, and the battery or device must be doused in water or other non-alcoholic fluid in order to do so. Next slide, please. Lithium batteries are not one thing. They come in different sizes, constructions, and chemical compositions. There are many different battery chemistries available, and the chemistry will dictate the specific nature of the electrochemical reaction that takes place in the cell. Lithium-ion cells are named after the chemical composition of the cathode. And if you hear terms such as lithium iron phosphate, lithium cobalt oxide, lithium manganese dioxide or oxide, this will give you an indication of the chemistry composition within the cell. But whether the cells are single or whether the batteries are single or multi-cell, and whether a thermal runaway propagates between cells, any cell failure can propagate to surrounding flammable material and create a wider fire, which presents a challenge within the cabin in order to respond. The next few slides that I will share are taken from an Airbus document, which is probably now relatively out of date, and I include the images only for illustrative purposes. Any inaccuracies are mine and not those of Airbus. Next slide. This image gives you an indication of the typical types of device carried every day in aircraft cabins that may contain lithium-ion batteries. E-readers, laptops, tablets, cameras, headphones, power banks, smart bags, and AirTags. There are many, many threats within the cabin in terms of lithium batteries. And in general, the larger the device, the larger the battery, and the greater the threat. Typical scenarios for an in-flight cabin fire involving a lithium-ion battery may be an overheating issue due to a battery being discarded or in a seat covered by blankets, pillows, and clothing, and unable to dissipate any heat, or a device being crushed in a movable seat if it becomes trapped in the seat mechanism. Next slide. Many permanently installed items of equipment or portable items of equipment within an aircraft will be powered by lithium batteries. Typically, these are lithium metal batteries, which are non-rechargeable and have a different chemistry and energy density to lithium ion, but are equally susceptible to thermal runaway. Next slide. And although the focus of today's presentation is predominantly on the cabin, we must not forget that many, many more lithium battery-powered devices may be carried in passenger luggage, in the hold, or as part of cargo shipments, and can represent a threat to the aircraft as well. That concludes my presentation for today. Thank you. Next slide.
Thank you so much, Lisa. We appreciate it. And now, dovetailing on your presentation, we'll be introducing Candice Colender and her colleague, Mark Vanoff, from the Airline Pilots Association. Candice currently provides, Candice currently provides staff coordination, liaison, and training support to ALPA's pilot assistance groups, which include Aeromedical, Canadian Pilot Assistance, Critical Incident Response, HIMSS, Pilot Peer Support, and Professional Standards. She also assists ALPA staff and leadership on questions related to cabin safety issues. Ms. Colender has 28 years experience in a broad range of aviation issues spanning research to development of safety initiatives, regulations, and security-related activities. In 2017, Candice was appointed as the lead of the High Energy Fire Training Enhancement Working Group as a part of the FAA's Air Carrier Training Aviation Rulemaking Committee. The purpose of the group was to recommend updates and improvements to current training and guidance around response to high energy fires that can occur in occupied areas of the aircraft. The High Energy Fire Training Enhancement Working Group submitted their recommendations to the FAA at the end of 2018. She is assisted again by Mark Vanhoff, who is a senior staff engineer at ALPA.
Good morning, good evening, depending on where you are. First, apologies. Mark Vanoff was unable to participate in the presentation today, so I'll present for both of us. So next slide, please. Very quickly, I wanted to talk a little bit about training aspects. ICAO requirements are evolving regarding lithium battery fires, data collection, and containment products. Now, our presentation is actually going to build on pretty much everything that Lisa talked about. If you think about it, when Lisa was explaining the fires, realistically, what we're going to talk about is that these fires, lithium battery fires, can be more explosive, more violent, hotter, they burn hotter, and then, of course, they have more toxic smoke. Next slide, please. So one of the things that we wanted to talk a little bit about is the HEFTE, the High Energy Fire Training Enhancement Working Group. Information in Lisa's presentation talked about that the mainstream understanding out there was that there is a lot more devices these days. But when we did this group, that was tasked in 2017, the reality was we did not have as much information that we have right there. And one of the big things at that time, we actually made an assumption that each passenger on an aircraft was carrying anywhere between 2 to 3 lithium ion powered devices per flight. So if you think about that, that is 2.3 billion devices on those flights in 2017, where we were looking at this information. One of the things in the US that we had discovered was that although we had guidance to the regulators, from the regulators to the air carriers about firefighting, the reality is firefighting experience has gone through different reiterations. We started off originally assuming that the fires that would be fought in the cabin were those that were accidentally lit by passengers in the lavatory trash receptacles, right? Extinguishing the cigarette. Then we started putting in more information about electrical fires. And that would have been as we got more galley equipment on board aircraft, that we would have electrical fires in the galley equipment. Then firefighting focused on appropriate responses to hidden fires, those behind the panels of the wall. And eventually we had some information regarding lithium battery fires, but it wasn't as extensive as what we needed during that time in 2017 when we saw more information coming out about lithium battery fires and the possibility of more events happening on aircraft. So basically, our guidance wasn't necessarily keeping pace with the training with the changing hazards and risks that lithium battery fires could do. So the High Energy Fire Working Group was tasked with sort of making those changes. Next slide, please. So one thing about that is I'm not going to go into a lot of details, but I do recommend at the bottom of this page, there is the rec where you can see all the different recommendations. We approximately made 7 main recommendations with multiple sub recommendations. So there was a lot of information. Now, the one thing about this training material that we created, or recommendations, was things sort of didn't change. What did change though, so the general firefighting philosophy: locate the fire source, fight the fire, move the passengers away from the area, coordinate the actions with the crew, monitor for reignition, and report the event. So that didn't change. But what did change, and what we didn't have at that time, again in 2017, and we said we were missing, was we needed more information on more specifics about high energy fires. In other words, the lithium battery fires that Lisa talked about. So some of the things was we had to try to look at what happens with devices that are designed to be waterproof, right? How do you cool the cells inside a device that doesn't allow water in, or any other liquid that's supposed to be cooling these things? One additional thing that we kept saying, recognize the different type of fires, is that lithium battery fires, or any of these other fires, that we had to have cautions put into the information about approaching or opening compartments when it's suspected a device is in there going into thermal runaway. It's completely different than our regular firefighting. And then another big thing that we had recognized wasn't necessarily in the guidance at that time was the volume of toxic smoke and fumes that could be emitted from these types of device on board the aircraft. So that also needed to be done. And then we also put in some information related to flight deck electronic flight bags. And a lot of the discussion was in the flight deck, we have some devices that are mounted, and then some devices that aren't necessarily mounted. So how do you go about making those type of changes? Where do you move them? How do you fight these fires? Again, but all these recommendations are online, so I do recommend that you go in there if you want to. That is the way carriers should be changing, creating some of their training. Next slide. So I'm not going to go through every single thing about this, but I think for the accident investigation world, I think one of the critical things that we need to understand is that accident investigation can actually drive change. In 2006, UPS Flight 6 was going into Dubai, and in Dubai was on takeoff. And on that particular aircraft, it had approximately 280,000 bulk shipped batteries that caught on fire. So that aircraft was destroyed. So from 2006, when this accident occurred, in 2016, we finally got a change in the ICAO Dangerous Goods panel that said any batteries being shipped in bulk, in other words, bulk shipped, could only be shipped at a 30% state of charge. You guys, this is a huge, huge victory for the industry. So it does show that there is change that is possible from accident investigation. And if you think about it, again, originally in 2006, 2018, 2007, when we were doing all of these changes, we didn't even have the number of electronic devices that we do today. Again, one of Lisa's graphs showed the extensive number of how we have an increase in these types of devices. Additionally, on this slide, it does talk about in January 2026, in the future, one of the things that will be happening is that the other devices being shipped will need to be at 30% charge. Right now, we still can ship some items if they are either inside or packed inside a device or shipped in the device. In other words, think about your iPad that has the battery inside, or think about a charger or something, a blower that has the battery, but it's packed inside the box, not necessarily installed in device. Those can all still be shipped currently at 100%. But in January 2026, those will need to be changed, and it will need to be shipped only at 30% state of charge. Again, the purpose of this slide is just to say we've had a huge, huge victory, and accident investigation drove that change. Next slide. Next slide. So one of the things that, just to continue on, is ALPA does watch data from two different sources. We watch the data regarding lithium battery fires and any of this as part of our dangerous goods group to figure out what's happening out there. So one of the sources that we are watching is this FAA guidance. And down at the very bottom, again, there's another link that talks about some of the data that we see. So this website is actually pretty good. It actually has information all the way back from 2006 until today's May 2024. So this information on this particular site, the numbers are 530 verified incidents. This is a required reporting mechanism in the United States. So this data is actually required to be collected. And it has actually sort of changed over the life of the collection, just so we can keep watching it. But it does collect information for incidents that happen on board the aircraft. So we have 387 on passenger aircraft if you wanted to actually drill down in some of this. So all of this is a dynamic site if you go to it. Next slide, please. So the other data source that we look at, or data set that we are also watching as part of our dangerous goods group, is that we're watching this other group called TRIP. It's the Thermal Runaway Incident Reporting. And TRIP was actually sort of set out by an advisory group originally. Now, those airlines that you see, actually the difference between TRIP and the FAA is that TRIP is a voluntary group. And the airlines listed there have agreed to participate in this voluntary reporting. This slide is a little bit incomplete because in April 2024, TRIP actually got a few more participants that are going to have verbally agreed to participate in submitting data. Next slide. So one of the things that the difference, and this is from this is from TRIP data. This data from 2023 had 115 thermal incidents from 19 carriers. So 90 of those incidents were in the cabin or in carry-on baggage. 12 incidents were in checked baggage. That particular database didn't show anything necessarily in the cargo hold, but they also collected information from cargo flights. So cargo-only flights, they had 13 incidents, but they didn't show any crew or occupant injuries. So although the data is different, again, one thing you need to understand, the FAA data before was mandatory reporting, and this is a voluntary reporting. But it does give us a really good information on some of the things that are happening in the cabin, or in this instance, in cargo flights, about what is happening. So next slide. So one of the things that I think is pretty interesting on this slide, and this is again from the TRIP database, is if you look on the far left, this gives us a little bit more information on exactly what type of fires we are seeing or incidents we are seeing. And this one shows 35% of the thermal incidents involved e-cigarettes. That's that far left. So it has a number of 40. So as you drill down even more into that 40, in their information that they had been able to gather, 18 of those incidents were actually from one particular manufacturer of those type of e-cigarettes. So even that allowed them to say, okay, you're having a hazard with your particular device. So what this shows is really is that there is a lot of information out there where you can break down the events. We still do know that in looking at some of this data is that we have information is saying we're still getting 1 to 2 incidents a week in the US. Again, FAA data was collecting only that on the aircraft, whereas trip to trip is curb to curb. Next slide, please. So one of the things I want to talk about a little bit next on the next slide is basically when we were starting all this information in 28, whatever it was, we did not have a lot of information also about fire containment products. And the issue had generally been at that time that the air carriers were just putting products on that they had chosen would work to combat and or contain these electronic fires. And we saw how versatile and how explosive and different these ones were. Again, we're still doing the same information, locating the fire source, fight the fire, move the passengers, coordinate actions, monitor for reignition, and report it. But the addition, so in the FAA guidance, there also wasn't a lot of information on how you respond to these. So there, we started to say, okay, if the carriers are gonna put these containment bags, kits, whatever you want to call them on board, we actually need to have some better guidance of what those products look like. Next slide, please. Actually, one back. Sorry. The one thing I do want to point out on that last slide, sorry about that, is at the very bottom, the PED fire videos on the FAA fire website, item number 5. There is a link to that. I really do highly suggest that if you are looking for information or you want information on the training, we have multiple videos on that website that were developed as part of the Hefty group and as a way to kind of get more information out to individuals, operators, regulators, anyone, just so that we could say that these are better training aspects. Next slide. So the containment bag considerations or products, whatever you want to call it, again, we originally saw way back then when we started the Hefty work that carriers were just putting these products on. And also one of the things that they weren't doing necessarily is they were not training doing hands-on training on their products. They were just putting them on and they would issue a memo or something like that. Just says, go in, here's how you're going to fight these fires and here's how you take care of it. So we really needed additional information on what that looked like and how that was going to work. So we also started working on some information for these containment bag considerations after that work. Again, it's all sort of building on everything that we saw. Again, going back to everything that Lisa presented to us, we didn't necessarily have back then. So we needed more additional information. The effectiveness of the products are important, but it's only a small part of the puzzle. So when you're doing your investigation, these are also going to be things you're probably going to look for in your investigation. Next slide. I'm going to keep us on time. So present to the wrap up, one of the things, again, we looked a little bit about training aspects. All of these are various things that you can use as an investigator. It's going to help build your case. And it's also going to it could create change like we saw at the ICAO DG panel. And then we also saw the different training enhancements for cabin crew, where we kept emphasizing that you had to have hands-on, you had to have a different understanding of what was going to happen. So all of these things can be used by the investigators to affect change. One example that I think is actually interesting is during the FAA when we were creating these fires for cabin crew to fight, as again, just understanding the nature of these fires, that we had we had a runaway laptop in an overhead bin, and the fire was so hot and burned so quick and so explosive that the bin actually stopped. We could not open the bin after the fire. So we had to have bring the fire department in actually to open up the bin. But again, that just shows the nature of why it's important that when you do your investigation, you look at all of the aspects of it. Are they doing the hands-on training? What information are they using? Is there, data collection? What is the carrier training on? And then what products are they using? And with that, exactly on time. Thanks.
Thanks very much, Candice, and apologies, I've had to step in for Joann. She's having a few power issues where she is, so I've just taken over for 1 minute. So just the one question came in on the chat in relation to lithium-ion batteries. Are batteries also tested for aviation use in cool or cold conditions? So I don't know if Lisa or Candice, you'd like to take that question.
I'm going to defer to Lisa.
So I believe exposure to cold environments is also part of the testing if the batteries are intended to be installed in aviation equipment. I haven't got the precise details to hand, but I do think that's included in the abuse testing and purely just environmental testing as any aviation equipment would be exposed to.
That's great. Thanks, Lisa. And I think that's all the questions we have on that, and we are bang on time, so we'll keep going. So our next presentation, our final presentation of the afternoon, is by Dr. James Blundell from Cranfield University, and he's going to speak to us about some research work that's been done on disruptive passenger behaviour and the impact on cabin crews in terms of their own well-being and flight safety. So I'll hand over to James. Thank you.
Hello, I'm Dr. James Blundell. I'm a human factors researcher at Cranfield University. My main interests are human performance, both understanding how we might develop human-machine interfaces to improve performance, but also to understand the contributors or the inhibitors of performance that we might encounter. So I'm really pleased to be able to talk at this Cabin Focus ISASI event today about the research I supervised last year on the impact of disruptive passenger behaviour upon cabin crew well-being and their safety. As mentioned, this is research that I supervised, and the real kudos goes to Alexander Roche on the left, who's an experienced European dispatcher and senior cabin crew member, who I was really fortunate to supervise on his MSc thesis at Coventry University, where he wanted to explore the nature and the reasoning behind the spike of air rage events that we were seeing across the globe and in Europe during the time where air travel was beginning to pick up again towards the end of the pandemic. I'd also like to say thank you to Dr. Erin Chernak, who collaborated with us on this project, and she has previously been a founding chair and professor in the Department of Behavioural and Social Sciences at Embry-Riddle. So as mentioned at the start, my main interest is human performance, and in relation to cabin crews, what we need to do is consider what their role is to adequately define what their respective performance is. And for cabin crew, their role is quite interesting because it's a role that encompasses this unique and frankly quite peculiar duality that I'm pretty sure doesn't exist in many other working environments. So it's a role that is one part hospitality, ensuring that passengers are comfortable, that they're having an enjoyable experience whilst on board, and it's part safety. And critically, that safety aspect of the role involves both providing safety relevant information to passengers, and as we've seen at the start of this year in Japan, and likely during the different turbulence events we've seen in the past few weeks, they are there to maintain the safety of the cabin in challenging and uncertain situations and expedite evacuation if necessary. So what we know from psychology and from human factors is that our performance is impacted by our well-being, our mental state. And in this research, we really wanted to look at how the well-being of cabin crew in Europe was impacted by exposure to disruptive passenger behaviour. Now, these behaviours can encompass a wide range of passenger non-compliance behaviours that are quite frequent and relatively moderate compared to these more worrisome forms of disruptive passenger behaviour that cabin crews may have to contend with, that take the form of verbal and sexual aggression and threats of violence. And as a quick example, here's a video that was doing the rounds on Twitter and LinkedIn, where an intoxicated passenger flying between Dubai and Islamabad created this chaotic situation in flight. The cabin crew were physically assaulted, as you can see, and they were required to restrain the passenger in this instance. So we do have some really good research that show the factors that increase the likelihood of these behaviours occurring include things such as whether or not the passenger is intoxicated, as highlighted in this video. We also know that the level of the passenger's anxiety they're experiencing can change the likelihood of these behaviours. We also know that social group characteristics and the corresponding social norms of that individual can play a role as well. And whilst we do have some really good research to describes the likelihood of these events, what remains quite sparse is our understanding of the impact of these behaviours on cabin crew, on their well-being particularly, which is unfortunate given the prevalence of disruptive passenger behaviour and its impact on safety. For example, according to EASA, the safety of commercial flights is jeopardised by disruptive passenger behaviours every 180 minutes, and approximately one flight per month is forced to conduct an emergency landing. So the purpose of this research was to conduct an exploratory investigation to understand the prevalence of disruptive passenger behaviours in Europe and their impact on the safety and well-being of cabin crew. Given the time that Alex was doing this research for his thesis, we were interested in novel stressors and contributors to these behaviours, particularly looking at COVID-19 given the time period. And lastly, what we wanted to do was to provide some solution-orientated recommendations that arose from the cabin crew themselves through speaking with them. And these recommendations were aimed to reduce the prevalence of disruptive passenger behaviours occurring, and also look at mitigating their impact should they occur upon cabin crew safety and well-being. The work Alex conducted involved using interviews with a diverse range of European cabin crew from various European carriers. He did 24 interviews in all, and from those interviews Alex transcribed them, leaving us with approximately 800 minutes of audio to work with in our transcripts. And using these transcripts, we conducted a thematic analysis, which is a really popular method of analysing qualitative research. It allows you to provide a hierarchical thematic structure to what's been discussed in the interview, so you can identify what the prominent and reoccurring themes are that have come up through the discussions with different participants. From this analysis, 3 primary themes were constructed, each of which I'm going to go through in the next few slides in turn. First being, what were the experiences that cabin crew had, what were the nature of the disruptive passenger experiences they had. The second was looking at how these events had developed. So according to cabin crew, what were the contributors to the occurrences. And finally, and where I'd like to spend most of this talk, is cabin crew well-being, coping and mitigation. So how did these experiences impact their well-being? How do cabin crew cope with the emotional fallout from these experiences? And importantly, what do cabin crew believe to be effective methods for reducing the frequency and impact of disruptive passenger behaviours? Beginning with the experiences, with describing the experiences that cabin crew had encountered, general non-compliance of well-known regulations was seen as a frequent and was considered a standard normalised behaviour by cabin crew. For instance, the frequent flaunting of smoking bans. A novel form of non-compliance reported in this study was passengers' evasion to complying with mask wearing and other pandemic-related policies, which the cabin crew were required to enforce. Participants also talked a lot about the different forms of abuse they had experienced, the more extreme experiences of disruptive passenger behaviour. And the experiences that came up were the 3 common forms that have been reported in previous studies, those being physical, sexual and verbal abuse. For instance, a third of the cabin crew reported experiencing Physical assault and harm from passengers, and likewise experiences of sexual abuse were prevalent, likely attributed to the marketing-related sexualization of the job that's occurred over the decades. Unsurprisingly, experiences of verbal abuse were prevalent. In fact, all 24 of the participants in this study reported having experienced aggressive verbal exchanges with passengers during their careers. Whilst many of the participants in this study considered passenger reluctance to mask wearing to be an additional form of general non-compliance, as I mentioned a moment ago, a third of the cabin crew here considered this behaviour to be a form of abuse as well, as it heightened the virus contraction risk that the passengers were exposing them to. And finally, what we were interested to hear from our participants, the cabin crew, was how they perceived the change in frequency of disruptive passenger behaviours to have been during the pandemic, or towards the end of the pandemic, when more people were flying. Here, all the participants were unanimous that the requirement placed on them to enforce pandemic policy had led to this sharp increase in disruptive passenger events that we've seen in various reports worldwide. However, what we did get was this mixed picture on the severity of the behaviours that were being encountered. Some said that behaviours had gotten a lot worse from passengers, or there'd not been much change at all. And in some cases, cabin crew had said the behaviours of the passengers had actually gotten better. This seemed largely to be due to the region in which cabin crew were flying. Several drivers of disruptive passenger behaviour were noted, the first being intoxication of passengers, particularly occasions where passengers arrived on the aircraft already inebriated. Cabin crew talked about the higher levels of societal stress that the pandemic had created in the situation, and so had developed this situation where many passengers were coming on board already with these elevated levels of stress that primed some of them to express disruptive passenger behaviour. The topic of perpetrator gender often arose when we were discussing disruptive passenger development with the cabin crew, and here the majority of participants voiced that males were far more likely to be perpetrators than females. Though there was this common trend from the participants in what they were saying that suggested that the different genders often expressed the difficult behaviours differently. For example, female disruptive passenger behaviour was more often characterised by non-compliance, whilst male problematic behaviours was often the more severe abusive forms and aggressive forms of disruptive passenger behaviour. And for the final theme, the crew shared their affective states during and after the incidents they had encountered, their perception of workplace safety, the coping strategies they used to process the unpleasant experiences, and the suggestions to deter or obviate future disruptive passenger events. So in terms of emotional well-being, the affective states of cabin crew that were most commonly reported were anger, annoyance, fear, and powerlessness. Furthermore, the majority of cabin crew mentioned that negative emotions were experienced over a protracted period following the encounters. They were often taken back home or back to the hotel, and I was particularly worried by some reports from participants that sounded very much to me like PTSD-like episodes, whereby participants recounted experiences and moods and emotions that they had felt during the initial disruptive passenger event. For personal safety, it was found that male cabin crew very infrequently felt that their personal safety was compromised, whereas female cabin crew mentioned times that they had been fearful for their personal safety, with one participant going as far to say that they only felt truly safe when an air marshal was present on their flight with them. Participants reported using a range of adaptive and maladaptive coping strategies to deal with their feelings following disruptive passenger behaviour. The adaptive strategies were most often characterised by discussing their feelings with families and colleagues post-event. Interestingly, whilst all participants were aware of their airline's peer support systems, only one had used it out of the 24 we interviewed. though they did voice that this support had been very useful to them. The maladaptive coping strategies, the unhealthy coping strategies, were observed in the form of denial, repression, self-isolation, substance abuse, and the normalization of disrupted passenger behavior. And for the last sub-theme I'd like to talk about today is about prevention and mitigation, where participants gave their thoughts on how airlines or regulators can improve the current situation with disrupted passenger behavior. So at the airline level, participants suggested an improvement to training efficacy for dealing with disrupted passenger behavior, and that their pre-flight briefings could include greater clarity on the strategy that they would employ should disruptive passenger behavior occur on the subsequent flight. At the regulator level, participants were often voiced how strict alcohol bans would be beneficial, and also that the severity of the consequences should be increased, or in the very least, the consequences should be more clearly communicated to passengers in order for these to serve as more effective deterrents. To conclude, this study, we reported that disruptive passenger behaviours emerge through a random and complex combination of several factors. Like many studies in the past, these things have been reported, but what's unique in this study was that we were able to look at emerging contextual contributors to disruptive passenger behaviour in the form of the post-pandemic environment, particularly late pandemic, where cabin crew were required to police different pandemic policies and how those contributed to disruptive passenger behaviour occurrences in Europe. We found that these disruptive passenger behaviours occurred with increased frequency following the post-pandemic aviation recommencement, and we found that these behaviours were detrimental to flight attendant well-being and safely. And these minor transgressions, particularly furthermore, minor transgressions had appeared to become widely normalised and downplayed by cabin crew. And there was a lot of discussions, recommendations around the improvement of training and pre-flight briefings, and that stronger deterrence would be beneficial in deterring potential perpetrators. Just to finish this presentation, I'd just like to discuss some future research we're looking at in Cranfield. So there's some excellent research that's been done in Trinity College, looking at mental health and well-being and burnout in the pilot population, and following on for this qualitative research with cabin crew, we kind of really need that level of research to be applied within this population as well. So there's a demand for that in order to ascertain whether the results we get from these sort of studies, these qualitative studies, can be extended to a wider population. So that research is really important, and hopefully we'll see some advances in that area in the years to come. In terms of trying to provide better support, not just understanding the problem, a few areas that are of interest to research at Cranfield and in Europe is looking at, firstly, how you support cabin crew to deal with chronic stress, dealing with continuous non-compliant exposure from behaviours from passengers. So we've done work at Cranfield looking at how we might be able to support pilots in this regard with chronic stress, looking at how you might be able to give them training in psychophysical resilience and coherence training. So that would be an interesting area to explore here, to helping cabin crew deal with that chronic form of stress they're encountering through dealing with passengers and non-compliance. And the last area of research that would be very valuable in this area is looking at how we might be able to support cabin crew, not only dealing with disruptive passenger behaviours, but emergency or unexpected situations in many different regards, is looking at how you might be able to improve their training to deal with startle and surprise as we've had quite a bit of research, especially in TU Delft and Saparu and Toulouse in Europe. These universities have done some really good work with pilots looking at how we might either detect when somebody's startled and surprised during an emergency and help them to respond more quickly and more appropriately. We also look at how we might be able to help them recover as well from these instances as well. So there's lots of research and findings from the pilot population that I think would transfer really nicely onto the cabin crew population, which we could explore as well. Thank you very much for listening. If you have any questions about this presentation, feel free to email me or send me a message on LinkedIn. Thank you very much.
So we do have a couple questions from chat, if you have the time. The first one is, how were the participants and the research recruited to ensure that they accurately represented the wider cabin crew community?
Yep, that's a good question. So in this study, we did use Alex's wider network of professional contacts, given his experience his professional experience in cabin crew. He had access to a lot of cabin crew, both within his own airline, but also across a network of other airlines. So there was a lot of snowballing in this instance to get the demographic that we use, the sample that we needed for the study.
Okay. And the next question,
a survey would be more beneficial to look at the wider impact and whether or not these are effects that we're seeing in wider population of cabin crew across Europe.
the next question is from chat, and it's a two-part question. What are the regional difference in which cabin crew perceived unruly behavior? Has it improved? And what areas are perceived as particularly good or bad?
Okay, so I think I'll struggle with the first part, given I don't feel we had enough data in this study to argue to answer that question clearly at this point. We had regional differences in our cabin crew, but I would really be hesitant to comment on that without a much larger sample to be able to have an accurate picture of what's happening. We're looking at trends in this analysis rather than at quantitative objective measures or large data from surveys. And the second one was about what's good and bad.
Yes.
The second question about what was good, the good behaviors or the poor behaviors.
Yes, exactly.
I'm afraid I can't remember that off the top of my head. Fortunately, this research is in the process of being published. So if you are interested in that question, please do look at the paper when it is published, when it will be open access as well. So I'll make sure that's shared, or Alex would be able to answer that question, but I don't feel I can answer that right this moment.
Okay, and I think you partially answered the final question that we have, but I'll put it out there again. Is there a relationship between the social culture of passengers and the propensity or severity of the disruptive behavior that's exhibited? Is there a relationship between the social culture of the crew and their experience?
Yeah, I saw that one pop up from Ed
Yeah.
as I was speaking. Yeah, I don't think I'll be able to answer that one at this stage, unfortunately, Ed. But yeah, I'd love to talk to you more about that afterwards.
All right. Well, thank you so very much for joining us. And this concludes our presentation for this session of Focus On. We'd like to thank you all for your time. And it's our hope that this session was informative to everyone who participated. I would be remiss if I failed to thank the presenters, as well as Kate Fitzgerald and Brian McDermott, and all of the assistants from ISASI who have arranged in facilitating this session of Focus On.